Let's begin Chapter 12, Stoichiometry. In the last couple of chapters, we've been talking about writing formulas from words and using formulas then to change the formula to the name of the compound or the molecule. Then we spent some time on reactions, types of reactions, and we worked on balancing reactions. And you can see here that we have a balanced reaction, and we have two potassiums reacting with two waters to form two potassium hydroxides and two hydrogens. And we've placed coefficients in front of each of these. 2, 2, 2, and here is an implied 1. And we do that because we know that we never create or lose matter. And so here we have two potassiums. Here we have two hydrogens and also two hydroxides. I've mentioned to you before that sometimes when you're balancing equations, it's good to look at like switch water to HOH instead of H2O, because over on this side of the equation it shows up as OH and makes it a little easier to balance. Here we have two potassiums, here we have two hydroxides or OHs, and here we have two H's. So we can see that we have a balanced equation. We started with the same number of elements that we ended up with. That's the purpose of putting these coefficients in front of these molecules, so that we know that we neither create nor lose matter. And I've explained to you that when you have a chemical reaction ongoing, that you can think of it as having an abundance of anything that you're working with or creating. It's not like you have only one molecule on the shelf to work with. What I want to introduce with this slide is the idea of conservation of mass. And so we've done molar masses before, and here I've quickly pre-calculated the molar mass of each of these molecules. And as you remember, you go to the periodic table and you look up the mass of the elements. And potassium is 39.1, so 2 times 39.1 is 78.2. I multiplied it by 2 because of the coefficient of 2. 2 times 18 is 36.0, and if I add these two together, I get 114.2 grams. And over here on the product side, potassium hydroxide has a molar mass of 56.1. You can quickly stop this video, go look at the periodic table and see that I added potassium 39.1 to oxygen 16 to hydrogen 1 and got 56.1. I multiplied it by 2 because of the coefficient, and I get a molar mass for these total potassium hydroxides of 112.2. And then hydrogen has a molar mass of 1. I have two hydrogens in this. Remember that the hydrogen is a diatomic atom that when it exists naturally by itself, it exists as 2. We talked about that you have bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, that when they exist by themselves, exist diatomically. I gave you a way to remember that as Dr. Brinkelhoff. Anyway, back to the molar mass. This is a molar mass of 2, and if I add these two together, I get 114.2 grams. So I'll end this slide with the idea that when you have a balanced equation, you start with the same number of elements that you end with, and also that you have a conservation of mass, that the mass you start with will be the mass that you end with. On this slide, I want to make you more aware of what you're looking at when you're looking at a balanced equation. So we have potassium reacting with oxygen to form potassium hydroxide. And I think you're probably pretty comfortable that 4 atoms of potassium is reacting with one molecule of oxygen to produce 2 molecules of potassium hydroxide. But we've talked about this before, that if I were to take each of those and multiply it by Avogadro's number, 60 to the 23rd or 60 trillion, just a huge number, we would end up having then 4 moles. We'd end up having moles of each of these ratios. Instead of just 4 atoms to 1 molecule to 2 molecules, we'd have 4 moles of atoms to 1 mole of molecules of oxygen to 2 moles of molecules of potassium hydroxide. So we have these are the moles that are reacting with each other to produce the moles of product. I want to also introduce an idea that if I had 4 moles of potassium and an excess, more than enough oxygen that it would be there available for the potassium to interact with, then I would produce 2 moles of K2OH, or potassium hydroxide. But let's change the numbers a little bit. Let's say I have 8 moles of the potassium, but once again I provide an excess of the oxygen. Then I've multiplied this by 2 to get 8 moles of potassium. So if I multiply the K2O potassium hydroxide by 2, then 4 moles of potassium would produce 4 moles of K2O. But for that to be true, you have to have an excess of that oxygen. So when we're doing these sorts of equations, it will be stated in the problem that you have an excess of any of the reactant that is not being addressed in the problem. Another example is if I had an excess of potassium and I had 10 moles of oxygen to work with, then I could produce 20 moles of K2O. This ends up being very important for like chemists in the laboratory, because quite often you're trying to produce a set amount of perhaps product, and you want to know how much of one of the reactants to start with to give you that product. And that's where this is going to show up in the chemistry lab, and then will also show up with the problems that we'll be doing later on in the chapter. This picture with what I've just been talking about, that you have nitrogen reacting with hydrogen to form NH3. Just interestingly for you, that's also called ammonia. Also, be aware, just remind yourself, NH3 is diatomic, nitrogen is diatomic, as is hydrogen. So when you start writing these problems again, remember all these rules I've taught you about how to write the different right here, very cleanly they just remind you that here you can address this chemical reaction as atoms. So you have 2 atoms of nitrogen reacting with 6 atoms of hydrogen to form molecules that are 2 atoms of nitrogen and 6 atoms of hydrogen. You can use the phrase molecules for your representative particle. As you remember, we've started to use that term months ago, representative particles. 1 molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of NH3. Just like in math, you can multiply these equations by the same number all the way through, and the statement is still true. So here they've multiplied it by 10, and you get 10 reacts with 30 to form 20. The ratio is the same. This is the important thing to get out of it. The ratio is the same. They don't add up mathematically, but the ratio relationship remains the same. And here, just like I did, they multiplied it by Avogadro's number and converted it to moles. And finally down here, They converted each of them to, multiplied each by the molar mass taken from the periodic table. The molar mass, the unit for it is grams per mole. So when you multiply 1 mole of nitrogen by its molar mass of 28 grams per mole, then it represents 28 grams of nitrogen. And you end up with, when you do this for the other reactant, the other product, you end up with the mass of the reactants equaling the mass of the products. Your homework for this section is to do numbers 39 through 41 on page 826. I've already done 39C for you. You are to attach this on campus. We've practiced doing that in class. There is a tutorial video on the bulletin board of my on campus if you've forgotten how to do it. Best wishes.